Alright, I'm going to start out as I usually do with my test equipment videos, taking a look at Chuck Penson's excellent book, Heathkit Test Equipment Products. I'm going to flip to the chapter on high voltage power supplies. Now, Heathkit's first high voltage power supply was the PS1, which came out in 1950. And this allowed you to provide a single high voltage supply with some regulation in the 50 to 300 volt DC range. It's essentially unregulated, but it has features that make the voltage reasonably stable for the intended application. A very low current power sourced into a vacuum tube circuit. In 1952, the PS1 was replaced by the PS2, which is a major improvement over the PS1, adding the much needed voltage regulation. Also, the entire output range is shifted up from 50 to 300 volts on the PS1 to 160 to 450 volts on the PS2. Then in 1954, the PS2 was replaced by the PS3, which is a significant improvement. The most notable change is that the output voltage range was made continuously variable from 0 to 500 volts. And it was also regulated as before. And then going to 1959, a slight overlap of 1 year overlap between these two, the PS4 was introduced, once again in 1959. It's not a replacement for the PS3 necessarily, which is why there's the overlap. It's actually a more capable power supply. It has the same high voltage regulated output as the PS3, but it adds an additional second power supply, which could be adjusted between 0 and 100 volts at 1 milliamp maximum as a bias supply for various tube circuits. And they also added a current meter for the primary supply so you could see how much current it was providing. The PS2 was replaced in 1962 by the IP-32, which is really just a cosmetic upgrade. The circuits are essentially identical. There are two different meter styles used on these, so this picture only represents one of the meter styles. Then the IP-17 came out in 1967 and was made for about 10 years. It is really the same circuit as the IP-32, but in a more of a benchtop style case. The only functional difference between the IP-32 and the IP-17 was that Heathkit added a 12 volt filament supply to the 6.3 volt filament supply that the IP-32 had. So it retained that, but it also added the 12 volt. And then finally, in 1977, the IP-17 was replaced by the IP-2717. Really just the same thing as a cosmetic restyling. And this unit was not replaced. It was discontinued in 1986, probably because its primary application was in vacuum tube circuits, and by that time people weren't doing much with vacuum tube designs where they could sustain a power supply dedicated to that type of work. So this video is going to be about the IP-17 in particular, and by extension the identical IP-2717. Alright, so here's the case half, or the case shells. It's a little bit bent up. And something really took a dive into this area, and it's not so apparent in the video, but something landed in there and bent some of those. One of the feet came off, the other ones aren't looking that great, so those will get replaced. The top isn't too bad except for some gouges like that. It seems to be pretty free of bends. And I'm going to clean these up, and I think I'll just give them a quick shot of paint. just to make them a little prettier. I have a little bit of this Rust-Oleum camouflage, whichever shade this is, the khaki. That's a close match to the original. So here's the main part of it, and it's had some modifications made which I'm only going to partially mess with. Obviously a lot of things have been added and subtracted over the years by previous owner or owners, but this is not an actual restoration. It's just to clean up some issues with it. I'm going to pull the handles off, and I'm going to try to deal with the denting. You can see how the front panel is bowed in there. Try to undo that a little bit without taking everything off of it. The binding posts are pretty grody, but these are the non-removable kind. The aluminum has been swaged at the ends so they don't unscrew. So I'm just going to have to address these with a toothbrush in situ, or some people would say situ. Sounds more like a sneeze to me. The back panel's also bowed in quite a bit. I'm going to take that panel off a little bit, although it has some parts glued to it by a previous owner, so I can't take it off too much. And try to straighten that. I'm also going to add a selector switch. Since this has been so far modified, I'm not worried about trying to keep it the original Heathkit way. I'm going to put a big selector switch up in this area so that I can keep this circuit and this, which were one of the add-ons, so I can keep it in there but switch it in and out of the circuit. So with all of that, I've got to do some partial disassembly. Okay, I've got those major parts, including the front bezel, sitting in the warm soapy water. I've peeled the Heathkit label off the back because I'm going to be using that area to put the toggle switch in, and I'll relocate it to a different area of the back panel. But in the meantime, I need to undo some crinkles and also dissolve the remnants of the old adhesive. So I've sprayed it with my Tech Spray label adhesive remover. I'm letting it soak for a little bit. Meanwhile, I have to address the sticky glop on the back of the rear panel, which, by the way, I've straightened already. That was actually pretty easy, easier than I thought it was going to be. I just got it up against the side of my bench here and kind of braced one corner here up against my rib cage, and the other corner with my hand here, and then just took a stick and put it up against the rear, and bracing the ends of the panel with my hand and the corner of my torso, I just pushed wherever I needed to, and then occasionally checked for straight using the same piece of wood, and that just took the bends right out. So that came out pretty good. Alright, here's a 3 PDT 2-position toggle switch that I bought. It's an Eaton/Cutler hammer part, so it should be pretty good quality. I bought this from Newark Electronics. It was the only place that had stock on them that did not have a minimum purchase, although I still bought 2 just because I thought it would be handy to have another one like this. It's rated for motor use, so it's really intended to be used in motor circuits, and all the spec sheets are all about its AC ratings. I contacted Eaton Tech Support for this particular product line, and they just said, well, there's no ratings on this for DC use, so you're going to have to interpolate, but we can't make a recommendation because we're not allowed to read between the lines. So, as sort of an easy way of looking at this, all these ratings here are, you know, if you're on a 250 volt AC circuit, it's good for 10 amps, 15 amps if you're on a 125 volt AC circuit. Then you get into horsepower. Is a 250 volt circuit, 3/4 horsepower motor, you know, and all the ratings are like that. But you notice that the ratings go up to 600 volts AC on a three-phase circuit, or 480 volts AC on a single-phase circuit. That tells me that the dielectric capabilities of this structure are good for that kind of voltage. However, it's not just the dielectric and that is involved. It's also the contact material and the way the contacts move when you're switching, and you know how quickly they move apart, and do they have a wiping action. There's all sorts of different things which influence the ultimate ratings. This switch is only going to get used when the unit is turned off. It's a mode switch. Do I want to use it with the extra output induction and capacitance, the output RC circuit that another owner used? Or do I want to use it the way Heathkit designed it? Which mode do I want it to be in? So you pick which mode. In my case, it's almost always going to be in the Heathkit mode. And then these switches here are not being, the switch is not being moved from one position to another while power is energized. So that gets rid of some of the issues. And all I'm really interested in is the dielectric capability of the switch good for up to 400 volts, which is the circuit it'll be in. And I think this indicates that it is. But if I was going to be switching this on and off, you know, an AC arc quenches on the half cycle, whereas a DC arc could continue indefinitely. On the other hand, this is an extremely low power circuit, and it's also regulated. It won't, and this will be on the output of the regulator. I think the chances of this actually continuing to produce an arc, or even arcing in the first place, is very small, and it should only happen if I switched it while the power was on. So anyway, I'm taking the chance that this is good enough by that rationalization. So basically I've got this LC, I might have said RC before, but it's an LC filter circuit that another owner has added. I'm going to keep it in there, but this switch here will be to switch into the LC circuit. So it either bypasses it or it goes through it. This next switch is to come out of that circuit. Do I come out of that circuit, or do I come out of the bypass? And then the third one is because I want the large capacitors in the LC circuit to be discharged when I'm not having that circuit in use. The third set of contacts here will be used to switch in a resistor to bleed that capacitor down quickly when I'm not in that mode. So I have to mount this switch. This is the inductor that the previous owner added. It's not an original Heathkit part. And these two big electrolytics that are glued to the back of the case, and they also have a smaller capacitor across them. Now these two, because it's the voltage rating on these caps is not up to 400 volts. I think they're 250 volts rated. So the previous owner put two of them in series, which is not something I would like to do, but you can do it that way. Assuming everything is pretty much equal between them, then they'll pretty much share the voltage. And then he's also got the smaller cap wired across those two in series. So the way he has it modified, this is the current meter. used only for the 400 volt supply. Normally this terminal goes straight to the positive output jack down there, and I think there was probably originally just a wire running across here and going down to there. But what he's done is he's come over here, and he comes around, and he comes up and goes into one side of this inductor, this choke, and then comes out the other side. Now the output side also continues on and goes over to this terminal. So you come out of the meter, you go through the choke, and you continue on to the ultimate destination. But you're also tapping off that point, the output of the choke, and going through down to here and going to this capacitor, which then has another wire going back around here and going down to the ground terminal of that circuit. So I'm basically going to be rewiring this thing so that it does exactly the same thing, but it has to go through this switch to do it, or it'll go the original Heathkit way, just straight from here through the switch and out to here. Going to keep these caps right where they are, going to keep this choke right where it is, and I need to have some place to mount this switch. Oops, don't drop it on the tube, Paul. I think the best place to put it is, I don't want to have to open the case to operate it. That's a basic right there. Really the only place that's available is back here. Now I can put it right above those two items down there. I could do that, and I may choose to do it that way. Or I could put it over to the side or over to the side, in which case it would make it harder to replace these tubes or pull them out if I have to replace or service them. So I don't really want to block the path. Putting it right in the middle would be better for that. I just need to make sure there's enough clearance. I made up this little piece of paper out of a post-it note. This is the size of the switch. And the depth of the switch inside the panel should be what I have here. So this little piece of paper represents the switch. And let's see, it's taller that way, so it's taller sideways. So the tall dimension is this way. So basically I can visualize where it's going to be and how far it'll stick out and so on. And I think if I mount it up kind of high in the case, there will be ample clearance below the switch before I get to the capacitors. And still, it's not going to be right up against the top of the case. And it'll easily be in between those two tubes, so that's where it's going to go. Okay, that switch is mounted in there. Lots of clearance around it. Looks good from the outside. The other thing I have to mount in here is this power resistor. It's a 4K ohm 5 watt in an aluminum case. It's pretty small, but it's more than adequate for the needs of discharging those capacitors down there. They will actually develop more than 5 watts, but only for a split second as they discharge. So the smaller resistor can be used. I actually charged this thing up a bunch of times in sequence and then discharged it through just a resistor on the output terminals. 1 watt wire wound 4K resistor, and you know, yes, temporarily it was dissipating more power, but it never even got warm, so this is more than adequate. In reality, I probably could have used like a 1/2 watt carbon film or carbon comp resistor. It probably would have worked fine, but I decided to take this junk box part and put it in here. Now the problem is that this has got such tiny mounting tabs on it. I don't have any screws. Even a 440 is way big for that. So I think what I'm going to do is glue this to something and then mount that something to the back here, probably right next to the switch. It's so small it should not impact removal of those tubes if I need to remove them. I got an even better idea, I think, and that is just to glue it to the side of the switch, and then it'll be right next to where it needs to be wired to. Okay, that's epoxied on there now. I just have to give it some time. It is tending to drift a little bit as these do. It'll slide right off of there on that film of epoxy if I don't do something about it. So I have to rig up something that'll temporarily hold it in the desired position. Alright, I've got my second coat of paint just sprayed onto the top and bottom covers. I forgot to straighten out the bent one before I started painting. Oops. But it's not a big deal. I can straighten that out without damaging the paint after the paint is dried. Meanwhile, I've used some satin black to paint the inside surfaces of the bezel, which were originally just aluminum or whatever pot metal this thing is made out of. I also forgot to straighten this one. Good grief. But it's only slightly bent, and I can bend it again without damaging the paint. And most of that paint won't show anyway. It showed because the front and rear panels were bowed, or the front panel was bowed in. It's just for the heck of it. I was mainly painting these corner brackets for the handles, which were a little bit scratched up. Alright, the paint is dry, at least dry enough to handle, and I've straightened out, oops, straightened out this part here, got all the kinks out of it, got it straightened out on the vents, and I've also straightened out the bezel so it lays flat. Okay, here's the existing circuit. Here's the ammeter. This is the input to the ammeter. The output from the ammeter flows over here, goes into the inductor. The one I'm marking, the input of the inductor. And then the output of the inductor goes to two places. First off, it goes to the positive output terminal, and it also goes up to the positive side of this electrolytic capacitor, which is in series with another one, minus to plus, so this acts like one big electrolytic. And then there's also a smaller capacitor across that bigger capacitor. And the negative side of the capacitors is brought through a wire to the minus terminal, output terminal, which is already connected to circuit ground for that particular power supply. That's what this is going to. So, schematically, you got the ammeter, you're coming down here, ignore the switch. You just come through the inductor, then you have a capacitor to ground, and then again ignoring the switch, you just continue on through to the positive output. So we have an LC filter there. Now what I'm going to be doing is adding this 3PDT switch. So 1, 2, 3, that's 3PDT, so 3 poles, double throw. And the double throw means that there are 2 active positions on each of the switches, this one and this one. So the switch can either be here or it can be here, and there are 3 of those, so hence the 3PDT. So I'm going to be wiring it up so the ammeter now goes to the common of the first pole of the switch, and the second pole of the switch, its common, goes to the plus output. And then the bypass position of the first two poles just gets jumpered straight together. So that provides the straight bypass to make it just like the original Heathkit circuit. And when that's in that position, when the switch is in the bypass position, the third pole of the switch shorts out the capacitors so they have no voltage on them. Now when we move the switch to the engaged position, now the bypass circuit is removed. We come from the ammeter, we come down through the inductor and with the capacitor to ground, and the shorting contact is opened up now, so the capacitors are no longer shorted. Then we continue on to the output. So pretty simple. I just need to come up with the most economical rewiring of this circuit. Of course, instead of just shorting out the capacitors, I'm putting in this resistor here so that the capacitors discharge through a resistance. And I'm planning on replacing all of the wiring. There's only a couple of them that I could salvage, like the one from the minus terminal up to the capacitors. Everything else needs to be replaced. And I'm replacing everything because the insulation rating on the conductors that the previous owner used appears to only be 200 volts, even though this is potentially a 400 volt circuit. So I have some wiring with 600 volt rated insulation, so I'm just going to rewire everything in this circuit. Okay, I've put the Heathkit label on the back, but instead of up here, it's down here now. And the label's actually centered left to right on the panel, and the switch is not exactly, because of its orientation, the fact that the two tubes up here are not precisely centered on account of the different sizes of transformers. I have the switch centered between the tubes, so it's not absolutely dead nuts with the center of the label here. Too bad. Anyway, so I have a clear label made on my Brother TZ printer. B+ output LC filter engage up, disengage normal or default position. Alright, here's the new wiring for the switch all installed. I had to run one wire through this other hole because I just couldn't fit any more through that one grommet down there. And there's the bottom view. I haven't touched any of the wiring in this area. This capacitor here is something that a previous owner stuck on. I believe it's just across the posts for one of the other capacitors. Maybe he felt it should be a little bigger capacitance wise, don't know. And there are the two capacitors that got added to help filter the B+ output if they're so selected by the switch I installed. And the freshly restored bottom is now screwed on. Okay, the work is done. The front panel cleaned up pretty nicely. Of course, I've got the freshly painted top and bottom, but the top is currently off and at a local sheet metal fabricator's because a friend of mine has one of these. It's actually the 2717, and he's missing the top panel, and I've decided to use the top of mine as a model for the sheet metal fabricator to make a replication of it for my friend, and until I get that back in a few days, I don't have a top for this one. Anyway, Everything cleaned up pretty nice in here. All the new wiring is tacked in place with little globs of gel CA glue that have been accelerated. And all this stuff turned out pretty neatly. Just for yucks, I'm showing the copy of the case shell for the IP-17 or IP-2717 that I had made. Neither the shop, well, the shop could have replicated this, but at considerable extra cost, so I didn't have that done. And I'm even putting in the holes myself, but I had them make it ever so slightly bigger, about a 32nd of an inch bigger on the inside dimension, just to make sure it wouldn't be too tight to go on. I'd rather err on the side of being slightly oversized than slightly undersized. And there's just a test fit. Actually, I've got it a little too far forward. Now I've moved it. I think it should be okay. Okay, I have the mounting holes drilled, although not cleaned up yet, and I've laid out a pattern for circular holes 7/8 of an inch each, which should, I think, approximate the amount of vent space that the originals had and still look pretty decent. I just need to open these up with my 3/8 inch hole punch, which is actually what is it? It's a 1/2 inch conduit knockout, really, but it's 7/8 of an inch. Well, I remembered how much I hate doing this for more than one hole. Just spinning it with the wrench and then having to back it out, and the piece that's been punched out always binds on the threads and stuff. It's a pain in the ass. But I have a friend who has a nice hydraulic one that goes about 100 times faster than this. So I'm going to go finish this up using his.
Yes, you're on your way.
Alright, that's been cleaned up. Hopefully it will get put to good use. Just a shot of paint on there and should look just fine. There's the final product. Alright, let's just take a little look on the inside of the power supply here. So the power cord comes in right back here and immediately goes right up through this hole. And the main power fuse, it's the only fuse in the power supply, is right here. It's a 1.5 amp slow blow fuse. If you have it wired for 240 volts, then it'd be a different value. This transformer here is the one that provides all the filaments, both the front panel external filament connections, as well as the, I think it's 3 different filament circuits for the tubes inside the power supply itself. So those all come out of this one transformer. And I've even marked it that way just for my own edification and reminding myself. This is the one that provides the high voltage for the 2 high voltage supplies. So that's what that transformer does. These 2 vacuum tubes here are the series pass tubes. They're what would in a solid state power supply be the series pass transistors, and there's two of them in parallel to handle the current, which is only 100 milliamps, so these are not really high current tubes. I believe that this type of tube was originally designed for use in like low power radio transmitters and things. They're pentode tubes, so they're maybe being used in a slightly odd situation here, maybe not. So then we've got the one and only circuit board, and there are 1, 2, 3, 4 tubes on it. These two are voltage regulator tubes. Each one regulates 150 volts across it. So between the two of them, they comprise a 150 volt / 300 volt reference voltage source. This tube here is another pentode tube, and it's being used as the error amplifier for the feedback on the main high voltage supply, the same one that these two tubes work with. So basically this is the one that looks at the reference voltage coming off of here, and it looks at the actual output voltage of the main high voltage B+ power supply. It compares them and decides what kind of a correction signal it should be sending to these two so that they actually do the regulation. So these are all part of that high voltage supply, and these are a reference. As the reference, these also provide the source for the other high voltage supply. That's the bias supply, or the one called the C- supply. And then finally we have a twin diode tube here. This is the one that provides the rectification for the same 150 / 300 volt reference voltage that these tubes go with. So even though they're on opposite sides of the board, they all are part of the same circuit. And a couple of these filter caps are used for this supply, and a couple of more are being used for the supply that goes with these, and then the remaining couple of filter caps are used for a reference supply that's also part of the main high voltage supply circuit. They actually provide an additional bias voltage source for these two tubes to operate with. These two trim pots down here, this is the one that is used to adjust where 0 volts would be on this knob here, and this one here is the one that adjusts where 400 volts would be on that same front panel pot. So the two of those establish the full counterclockwise and the full clockwise voltages you would get from this knob. The rectification, except for when this tube is used, is handled by solid state silicon diodes that are down there on the board, and there's a couple of more down in there that are kind of hard to see. And then a couple of small capacitors here and there, in addition to the electrolytics, and some carbon composite resistors scattered around. I don't think there's any wire wounds in here. These guys here, 1, 2, 3, 4, all the same value. Those are the bleed down resistors that are across essentially all of the electrolytics on this board, so that when you turn the power off, these resistors bleed those down. And they're all in series, because with the high voltage you end up with about 600 volts one side and minus 300 volts on the other side. So there's, close to, well, it's on the regulated side, so it's plus 400 minus 300. So 700 volts of charge, or a voltage in charge on most of these capacitors. It has to be bled down pretty quickly. So they're 1 watt resistors to handle the dissipation. And they're in the circuit all the time, whether or not you're bleeding down or not. So when you're not bleeding down, In other words, when the power supply is on, these resistors are also acting as a de facto load for the high voltage, well, for all of the supplies really, because they're across the whole thing. So yeah, these guys probably sit there and get moderately warm. I haven't checked them, but that's what they're doing for sure. These capacitors down here were an add-on by a previous owner, and I explained that elsewhere in this video. And then down here we primarily have the ammeter and another ammeter that's acting as a voltmeter. And then we have the two neon bulbs here and here, and then our two main potentiometers and the switch that switches between the two power sources, which one's going to go to this voltmeter. And of course the standby switch that's up here. This one switches the AC power to this transformer here. And I think that's about actually the resistors that are used around this switch here. They're the ones that cause the second ammeter here to act as a voltmeter. Those are wire wound, so they're precision resistors, as they would need to be to get a fairly accurate reading on the voltmeter. And really that's it. There's nothing else to this. So let's fire this thing up. Turn on my distribution panel here. Alright, let's turn this guy on. And immediately I get an indication that the voltmeter here is tied to the B side. If I move this switch, the other neon lamp turns on, indicating that the voltmeter is now tied to the C side. I'm just waiting for the tubes to warm up. Give them a moment. We can see the glow there of some of the tubes. Some of these are wrapped around with various materials inside that make it hard to see the glow, but this one's very apparent. Alright, that's long enough. So let's neither of these two supplies will output anything until the switch here is in the up position, the on position. Right now it's in the standby position, so the power transformer that supplies both of these two isn't even energized. Meanwhile, these filament outputs, and of course all the filaments on the internal tubes, are all energized through the other transformer, which is not controlled by this switch, only by this main AC power switch. So let's just take a look. Put my voltmeter on AC volts, and if I go here and here, it should be somewhere a little bit above 6.3 volts, which it is. It's almost, well, that's about 7.6 volts. Of course it has no load on it here. It'll drop down a little bit if there's actually a filament connected to it. And if I go over to here, now I've got about 15 volts. It should be, 12.6 or something like that, but again, no load on it. If I go across here, I'm back to nominally 6.3 volts. That's the way this is set up. It's with a center tap transformer. And I think the markings are a little bit confusing, because apparently this is the common. I think this is the common. Let's see. So from there to there gives me the full voltage, so the full winding is from here to here. And then when I go from here to here, I only get half of that. So that would suggest that either this or this is the center tap. And that's showing half of it too. So yeah, this is the center tap here, and this is the full winding. So the way they mark it there, they don't indicate that you can also get 6.3 volts off of, yeah, that's the full voltage. So it's a little bit of a misnomer, but if you just use it, if you want 6.3 you use this, if you want 12.6 you use this, that still works. It just doesn't tell the whole picture via the markings. Alright, let's put okay, so we're in there. I'll switch my meter to DC, and I've got the knobs turned all the way down. I'll turn the switch on, and this pot is tapered in such a way that there's relatively little voltage change until you get up maybe halfway, and then the rest of it's compressed in the rest of the knob. So let's first look at this. The meter switches here, so the meter here should be looking at this. So let's crank her up a little bit. So relatively small amount of change for quite a lot of change in the potentiometer. And right now we should be probably, I'm up to about 25 volts, and the pot is already over here. And we are getting approximately 25 volts, close to 24 volts. And it's negative because this is a ostensibly negative supply. This terminal is minus or negative compared to the common. So now the rest of this rotation should take me all the way up to 150 volts. I'm over here at about the 3 o'clock position. We're up to 75 volts. And it's reading about 80. And then a little bit more rotation takes me up, you know, somewhere in the ballpark of 125 volts. It's really only rated to 100 volts. Anything extra you get out of it's a bonus. So it's reading about 125 volts there. So that's working. I haven't put a load on it yet. And that slight lagginess in the meter is because of the previous owner adding the extra capacitors down there right across the output terminals, and with such a small load as this, that's what's bleeding down, not the actual power supply. Alright, let's go over this side. I'll switch the meter to the right so the B plus light comes on. Now we'll be looking at the red scale here, and also the milliammeter will now be in effect. Its maximum should be 100 milliamps from that little red arrow. And by the way, I've got the newly added switch in the back put in the normal position, so those extra capacitors and this choke here should not be in the picture. And this pot should be more linear than this pot was. So it's about 100 volts. Pretty close. About 200 volts. Pretty close. About 300. Again, pretty close. And then turning the pot the rest of the way, we should go right up about to 400. So this does not need calibration. The two potentiometers on the circuit board that establish 0 volts and 400 volts on this pot seem to be dialed in pretty well. Okay, let's take it back down, and we should have relatively little sag or relatively little lag on this. So when I turn it down, the voltage should drop pretty quickly. It's not instantaneous because there is still a little bit, there's almost no load here, and the small filter capacitors in the B supply with no load can hold the voltage up for a moment, and the internal bleeder resistors don't take it down right away. But it's a lot better than it would be with the other switch engaged, in which case it would lag a lot more because of those large electrolytics against the back panel. They'd be holding the voltage up without a load for a while. Okay, let's try putting a load on this. Alright, I have the B supply wired up to my DC electronic load, and it's set to maintain a constant current of 75 milliamps. And it'll also show me the voltage. Now I can't go any higher than about 300 volts on the power supply because this is rated for, well, up to 360 volts, but I've learned from experience it doesn't like it much above 300 volts. So let's start cranking this up. I'm going to turn the pot up until I get about 100 volts. Oh, I don't have the load actually engaged yet, which is why it's saying 0 down here. It is showing about 102 volts being applied, so I'm going to turn the load on. And now we see that the load here shows that we are pulling about 75 milliamps, and we're still at 100 volts. And the meter is showing pretty close to 75 milliamps. And we are more like 73 milliamps, so it is a little low. This isn't too inaccurate. And the voltage has not sagged. So let's crank her up to 200 volts. We're still at the same current here. And it's showing about 200 volts at 73 milliamps, so it's regulating pretty nicely. And I'll go up to 300 volts, but that's as high as I'm going to take it here. Showing good here. And again, we're doing pretty good in this department. Now, let's change the load. I'm going to increase the load to 70 milliamps. So I'm going to crank her up to 100 milliamps. And there we go. And that's what it's doing. The voltage has not changed. So it is regulating, and it is putting out the specified amount of current without losing regulation. So that's working pretty well. Now, I don't really want to test this supply in that regard. It's not really a regulated supply. This one isn't. It doesn't have any feedback. What it has internally is a reference voltage of 150 volts, and then it puts this potentiometer across it, and then the wiper of this is brought through a fairly high value resistor, I think about 22K or something, to these terminals. So if the load here changes, you know, there's nothing that's really going to directly monitor that and compensate. Yes, it is based on a regulated internal reference, but it isn't a true regulated supply, whereas the B supply is regulated and will change its regulation based upon load and other variables such as if the AC voltage coming into this changes. Although if the AC voltage, this will also compensate. It just won't compensate for changes in the load. So I'd say this power supply is working perfectly fine. Turn the DC off, and you can see that the voltage drops pretty quickly when we're under load. And there's the beauty shot. Alright, let's take a look at the manual. This is a reproduction of the original IP-17 manual. This one's done by manualman.com, who usually does a good job. The only complaint I have with them is quite a few manuals now they've used a comb binding that's too small for the thickness of the manual, so the pages bind. This one's okay though. It's right on the hairy edge, but it does work. Alright, so we have a somewhat more updated resistor and capacitor color codes table from some of the older manuals. Table of contents. Introduction. The IP-17 regulated high voltage power supply is a compact, convenient source of variable regulated high voltage, variable bias voltage, and filament voltage for laboratories and workshops. Separate panel meters are provided for accurate monitoring of the DC output current and voltage. All output binding posts are insulated from the chassis to allow the high B+ and bias C- voltages to be used as either negative or positive voltage sources. A meter switch permits you to monitor either the high voltage or the bias voltage of the front panel voltmeter on the front panel voltmeter. The special taper C- volts control provides a finer adjustment of low values for bias voltage. Built-in circuit protection prevents damage if the bias voltage output circuit should accidentally be short-circuited or overloaded, and the input circuit of the regulated high voltage power supply is fused for additional protection against overload conditions or short circuits. You will find all of these features plus the attractive compact styling will make this power supply a useful and valuable asset on your workbench. Then we have the parts list, a couple pages of it. A fold-out parts identification pictorial, the rear side of which has views of the front panel chassis components identified by their code numbers, which are used in the assembly instructions, and then with some of the wiring installed on it. Otherwise, we start out with the one and only circuit board. It's actually quite a simple circuit board when it gets down to it. And by this time, the instructions are more in line with what Heathkit used for the rest of the time they were in business. And you'd really think that with all these big honkin' electrolytic capacitors, what are there? 1, 2, 3, 4, 5, 6, that this has really got a lot of capacitance in it. In fact, all of these are high voltage parts, which is why they're big, but the capacitance is quite low. Mounting the binding posts and a couple of the rocker switches. Mounting some of the other hardware. Wiring up the front panel. Connecting the wiring harness, which is a pre-made harness. Mounting parts on the transformer subchassis. And then chassis assembly. And another fold-out pictorial. This one deals with wiring harness connections to the circuit board. More chassis assembly. Connecting the harness and transformer leads to the circuit board. That goes with that fold-out diagram. How to wire it up for 115 volt operation or for 230 volt operation. More wiring harness connections, in this case to the two main regulator tubes. A little bit more chassis assembly, mounting the rear panel, installing the knobs, test and adjustment. Final assembly, which just mostly involves putting on the handles and the top and bottom of the case. And then operation, it gives two examples, giving hypothetical vacuum tube circuit here, and showing how you might need a bias voltage applied to part of it and the higher voltage to another part of the circuit. Meanwhile, using the filament output to power that part of the tube, and then showing how it can be used on certain types of transistor circuits to provide various voltages. Then there's another fold out. This shows what everything on the front panel does, identifies everything and what it's for. And then on the rear of it, this is the X-ray view of the circuit board. A troubleshooting chart. Specifications. Let's see, just to go over it. For the B+ volts output, this is the actual high voltage one. 0 to 400 volts DC regulated, 0 to 100 milliamps continuous, and Heath was still doing this even though this is a kit coming towards the 70s. They're still using a small letter for an A, where today we would use a capital A for that. It can do 100 milliamps continuous, it can do 125 milliamps intermittent. Regulation output variation of less than 1% from no load to full load for an output of 100 to 400 volts. Output variation of less than plus or minus 1% for a 10% variation of the input power. Ripple less than 10 millivolts RMS. Output impedance less than 10 ohms from DC to 1 megahertz. And then there's a curve that shows that. The C- output 0 to minus 100 volts DC at 1 milliamp maximum. And then the filament voltage is 6.3 volts AC at 4 amps or 12.6 volts AC at 2 amps. And you can use both of those at the same time as long as you do not exceed 25 volt amps, 25 watts essentially. And then it has some of the mechanical things about the controls and the binding posts and the types of meters that are used and the tube complement, power requirements, physical dimensions. Then we get the circuit description along with a block diagram, a chassis photo of the top only, replacement parts list, 2 pages of that, and then finally the schematic diagram. Alright, let's look at the schematic for the IP-17. First off, we have 2 power transformers this one here, and this one down here. This one provides all the filament voltages, and there's actually 4 secondaries. This one is for the filaments of the circuit under test, and even though the binding post is shown centered here, it's really on this end of the transformer winding. So this is your 6.3 volt tap, this is your 12.6 volt tap, and there's the common. And then we have a filament winding which provides 6.3 volts to only the V3 tube, which is the one that actually handles the error amplification. And then another 6.3 volt winding for V4, which is this dual or twin rectifier tube. And then finally another one, 6.3 volts again, for these 2 big regulator tubes. The other transformer has 3 windings on it, 3 secondary windings that is. A center tapped one that's 600 volts AC center tapped. This one that provides 210 volts, and this one that provides 175 volts. The primaries are both wired so they can be connected up as 2 120 volt coils in series, or that's in the case of 240 volts, or 2 120 volt coils in parallel in the case you're running it off of 120 volts. So just by moving jumpers around on the transformers, you can operate this off of either type of voltage. And these points here, which are effectively across one of the coils, so it's always expected to have 120 volts, that's this A and the B, those get used up here in this circuit, which I'll talk about later. And then the schematic shows the way the wiring would be done for 120 volt use. Now the main power switch along with the fuse is here, and the instructions say that the fuse is provided for the for this transformer only, but the schematic shows that it is fusing both transformers, and the power switch switches both transformers. However, as long as you've turned the AC power on, this transformer, the one for all the filaments, is always on. Meanwhile, the one that actually provides the output power is controlled by the standby on-off or on-standby switch. The idea there is that you can immediately de-energize all of the power supplies except for the filament output by throwing the standby switch. Meanwhile, all of the filaments are kept energized, not only the ones in the power supply, but the filaments that you have hooked up in your circuit that you're working with externally. So it's ready to go at a moment's notice. As soon as you throw the standby switch on, then power is applied, and this immediately comes online. And you'll notice that there are essentially no capacitors in this circuit. There are a couple of little dinky capacitors down here, a couple of dinky capacitors up here, only 20 microfarads, only 70 microfarads, only 20 and 40 microfarads. So high voltages, but pretty small capacitances. None of those can provide substantial power for any length of time to the output loads. And that's why when you throw the switch here, it's presumed that the output goes dead right when you throw that switch. And when you turn it back on, it comes back up on in a split second. So let's look at this in pieces. So the bias supply, which is known as the C supply, or C minus, is used not only to supply the output, but it's also used to provide a reference voltage for the primary high voltage output circuit. So we have a twin diode tube here, so 2 plates which are anodes and one cathode. So with the center tap coming down to here, and then the cathode of the two diodes pointing up here, this becomes the positive of this supply, and this becomes the negative down here. And indeed, so this is full wave rectification, but using the center tap transformer. So it doesn't require a bridge, it only requires the two diodes in this rectifier tube. And you'll get roughly half of that. So you've got 600 volts across the whole thing, and you get about half of that after rectification. There's a small 20 microfarad cap from here to here, and then a resistor with another cap. This is what's known as a pi filter. Normally it's the other way around, so it kind of resembles the Greek letter pi. And that provides pretty good ripple rejection. And then we have two vacuum tubes of the voltage regulator type. Each one regulates at 150 volts, so it's like a 150 volt Zener and another 150 volt Zener in series. And since there's more voltage than that built across these capacitors, you essentially get 150 volts here and 150 volts here. You don't need a series resistance other than this one down here. So there's a total of 3,000 ohms of series resistance to drop any voltage besides what the tubes are regulating at. The two supplies each have a resistor across them. This one has 33K, this one has 50K in the form of the C- voltage control pot, which is nonlinear. It's has a taper to its resistance that favors the low end. So when you're dealing with lower voltages, a lot of knob turning changes the voltage relatively little. And then once you get up into the higher voltage, it's not considered as important exactly what the voltage is. So then a relatively small amount of this control makes a big difference in the voltage. So you can't dial it in quite as closely, but again, for the intended application, it wouldn't matter as long as you get in the ballpark. So this is all reference to this point, which is circuit common. And it goes to two terminals marked common on the front panel. And either of those can be tied to chassis ground, which is also earth ground through the power cord, if you want it to be. This is considered the minus 150 volts, and down here it's considered minus 300 volts. The 150 volt one relative to common is built across this pot, or applied across this pot, and then as you adjust it, you get a voltage anywhere from 0 volts to 150 volts. It passes through this current limiting resistor. There's a small, very small capacitor here to shunt any noise to circuit common, and then it's applied to the output jack. So that's the entire circuit there. Obviously it cannot provide very much current, and indeed it's only rated for 1 milliamp maximum. But for the type of circuit it's intended to power, that's more than enough. Now, looking at the primary supply, what's this goofy arrangement? It's not center tapped, it's only a single winding. It has a diode here and a diode here. How come there's two diodes? Well, this was in the earlier days of solid state or silicon diodes, and since the voltage is fairly high, the diodes they were using did not have a voltage rating that was high enough, so they used two of them in series. If these were to go bad now, you'd just replace them with one diode that would have a suitable voltage rating. This is also a voltage doubler, so the other side of the winding goes to the point between these two caps. So what happens here is on the positive half cycle, when this side of the winding is higher than this side voltage-wise, then these diodes are forward biased, and you just have this little circuit here. And you half-wave rectify this voltage and apply it across this capacitor here. So this is charged up to the peak voltage. And that should be roughly 300 volts across this capacitor. On the negative half cycle, now you have the same end of the winding, but now the diodes are pointing the other direction. They're going to this capacitor, which comes back here, so it's like a flip of this circuit. So on the positive half cycle, we charge this guy up to 300 volts, approximately. On the negative half of the power cycle, we charge this one to 300 volts. But because they're wired in series, across the two of them, you get approximately 600 volts. And again, the current draw is pretty small on this. The circuit's only rated for 100 milliamps continuous maximum. So it's considered that these caps have enough capacity to maintain reasonable voltage during the half cycle when they're not being charged through the diodes. And anyway, the output can only go up to 400 volts, so we are developing 600 volts here, which is 200 volts more than the highest output voltage. So you can actually have quite a bit of sag on the caps during the half cycle when they're not being charged, and it's still adequate. Well, the basic layout is just like any other regulated power supply. After we have our DC voltage developed, we take the positive supply, we run it through a series pass regulating element, in this case 2 of them to get enough current. So both of these are in parallel, and each one of them handles roughly half the current. So you come through here, these both act like variable resistances, and then you continue through here and go on out through the ammeter, which only applies to the B plus power supply, to that part of the power supply. It cannot be used for this part down here. And the circuit common is also the common of this supply, because it's tied into both this set and this set of rectifiers. So what we have essentially here at the simplest form is a filtered DC voltage going through a parallel set of variable resistors out through the ammeter to the output, through your load, and right back to the rectifier and filter cap. Very simple. Now these tubes here are pentodes rather than triodes, but they're being operated as triodes. Why didn't Heathkit just use triode tubes? Well, part of the reason is this circuit developed from one, many years older. They probably used the same or similar tubes back in the early 50s when the basic circuit was designed with the PS1. I don't know that for a fact, but I suspect there's that heredity to it. So they may have had a whole bunch of surplus parts on hand for these. But even if they didn't, the pentode has a lower voltage drop, so you lose less voltage through it than you would if it was a triode. I'm not sure that's important here when we have such a large voltage overhead. I'm not sure that the low voltage drop is their real reason for using it. They may have just said that to explain away the fact that they're maybe trying to use up some war surplus tubes or something. Anyway, so that's speculation. Anyway, so you have this extra winding. Once again, it uses 2 diodes in series, and then another pi filter, 2 caps and a resistor. So it's not regulated, but it's well filtered. The negative side is connected to the cathode of these 2 tubes, and then one of the grids in each tube is powered from the other side through these 100 ohm resistors. So that causes these tubes to behave like triodes, but with the lower voltage drop of the pentode. So that gets rid of one grid, and then this tube has 2 grids, one of which is tied to the cathode, so you can ignore that grid, the top grid. The only other remaining grid is the control grid down here. and those are tied together through 100 ohm or 1000 ohm resistors to this side of the V3, and that's what's actually going to control the voltage, or it's what's going to command these guys to control the voltage. Depending how much this one conducts will depend how much these ones conduct. In other words, how much resistance they offer to the passage of current going through, and hence the output voltage. So in order to have a regulated supply, you need to have some feedback. So that feedback is achieved here with this series of potentiometers and fixed resistors, and they come right from the output upstream of the milliamp meter, and that's going to have a really low resistance, so negligible. The other side, and these all form a big voltage divider, but notice that the bottom side of that does not go to the circuit common. Instead, it goes way down here to the minus 300 volt power supply. And that all has to do with the way these three tubes need to operate, in which voltage domain they're operated, even though the output will only be positive relative to circuit common. So this regulated reference voltage, minus 300 volts, is applied to the minus side of this big voltage divider. The B plus output's on the top, and then we tap off of the B plus voltage control potentiometer, which has a knob on the front panel, and that feeds in to the control grid of this tube here. So this is how it gets the voltage feedback, and it knows how much to conduct to control these guys appropriately. But we also have this intermediate grid here, much like we did with these, which has to be supplied with something, and that's done with this voltage divider here from the unregulated supply and back to the cathode here, and with a filter capacitor to circuit common. This may be rigged up in such a way that this helps it compensate a little better for variations in the line voltage. Not sure about that, but certainly the main feedback is this here, and when you adjust this, it determines how much this will conduct. But if the output loading changes such that the voltage sags a little bit, then the voltage here will sag a little bit. That influences what this does to control these guys, and it does it in a way that causes this to conduct more to counteract the sagging voltage out here. On the other hand, if the load here is lowered, the voltage here will tend to increase, therefore the voltage here will increase, and that commands this guy to change what it's doing so that these guys back off a little bit and allow a little less current to flow through, resulting in a reduction of the voltage, and by that feedback to regulate the voltage. This potentiometer here cannot have the full potential from way up here to minus 300 volts here, so parts of that are chopped out by dropping them in different parts of the regulator. You've got this 200K pot down here, that's the that's the 400 volt adjust, and then there's a similar pot up here, 500K, which is for adjusting the 0 volts. So when you adjust this guy, it determines when you have this one turned to the lowest position that you do get 0 volts on the output. And similarly, you adjust this one so that when this pot is turned fully up where it should be 400 volts, that you do get 400 volts. So these are adjusting the ends of the voltage divider such that the span here is appropriate for the desired output. And then these other guys in between 240K and 680K are additional droppers, which aren't adjustable, but it all works out if you do the calculations. And then you have this string of 27K resistors, 4 of them, and they're 2 watts, pretty hefty ones, and they're across this whole divider. Those are there for a dual function. One is they're a bleeder, so they help bleed down the supply quickly when you turn the standby switch off. So even though the only capacitance in this entire circuit are these two little guys here, by presenting a load here, it bleeds those down right away when you turn the power off way over here. The other thing is they help these guys work even when there's no load connected out here. They provide some place for the current to go so that these are able to this circuit is able to operate with a load at all times. This may be the only load that's in the circuit sometimes. And if you have this thing go from no load whatsoever to loading, there could be some transients, but by putting this on here, it eliminates that, or at least minimizes it. So that's the basic circuit here. Pretty classic in terms of its basic layout. The only novelty is that these days we're not used to seeing it done with vacuum tubes. So then the only remaining thing is the voltmeter. The ammeter is simple and it's only used on the main high voltage power supply, as I said before. This switch here on the front panel determines which of the two supplies the voltmeter is looking at. This is also a milliamp meter, and in order to make a milliamp meter work as a voltmeter, you have to have a series resistance. So when the switch is in the B volts position, the switch is over to the right here, and it connects this 400K resistor through the meter, and notice that the plus side of the meter is connected to the plus side of the supply, so the current will go through in the correct direction. And then it continues through this guy and comes back around and goes to circuit common. So the meter is put between here and here with a 470 or 400K resistor in series with it, so it gives the proper span. Now if you throw the switch the other direction, now we have circuit common up here, which is now the higher voltage, because remember this supply is a negative voltage, so the higher voltage is circuit common. And now it'll come through here, and the switch has to be imagined in the left position. It'll come up through here, come down, goes into the plus side of the meter. So we've achieved a polarity reversal here when we're measuring the negative supply. It comes out of that meter, goes through the left part of this switch, and through a 150K resistor. And in this instance, it goes to the C minus output. So same thing as with the B plus supply, it's just across the other set of output terminals and with a different series resistor to handle the scaling. There's one other thing that switch does, the third gang of the switch, and that is turn on the neon bulbs on the front panel to remind the operator which power supply is being metered by the voltmeter. So this A and B, as mentioned before, is just the voltage across the primary of this transformer, which is always presumed to be approximately 120 volts. So if you're in the switch is in the B plus position, that 120 volts is applied across this neon bulb, and that's the red one, and it's the one that says you're looking at the B plus supply. When you move the switch to the other position, now that 120 volts is applied across this neon bulb, so it lights up instead. They both have 27K current limiting resistors, otherwise they're identical. Now this one's marked as a shorting type sliding contact, and I think what that's supposed to indicate is that before it breaks this one, that it makes this one. I think that's what they're saying. I'm not sure why that's done, actually. I don't actually see a good reason for it. Certainly, other meters that Heathkit made that have the exact same idea here with neon bulbs saying which meter or which power supply is being measured currently by the meter don't do that. So it's not a technical necessity to do it. And I almost wonder sometimes if Heath got a good deal on a switch and it just so happened to have a make before break contact on one of the gangs, and they're like, yeah, we can use it on the neon circuit for this. I don't know. Again, speculation. But that's how this IP-17, and by extension the IP-2717, works.